Large language models are trained on massive data sets, but that training stops at a specific date. Once deployed, they have a strict knowledge cutoff. If you feed an AI a prompt, it holds facts in its working memory, but very quickly that memory fills up and spills over. It retains zero permanent memory of your proprietary data. When you ask a model a question that requires specific internal context it doesn't possess, it panics. It attempts to predict the next logical word based on its original training, which causes it to hallucinate false information, or it simply loses the plot and forgets the premise of your prompt entirely. This is the goldfish problem. It is the single largest bottleneck preventing companies from trusting AI with their enterprise operations. Intelligence requires context. Without a mechanism to store and recall long-term facts, an AI is effectively an isolated brain in a jar, completely disconnected from the reality of your specific business. The obvious answer is to connect the AI to a database. For decades, the standard way to store data has been traditional relational databases, organizing information into strict, structured tables of rows and columns. These older legacy systems rely entirely on syntax. To retrieve a piece of information, the database requires an exact one-to-one keyword match between the user's query and the text stored in the table. If a user searches for running shoes, a traditional database scans its grid for those exact 14 letters. It remains completely blind to a document labeled athletic footwear, even though the items are identical in reality. Human communication does not work like this. When we ask a question, we rely on intent, rely on context, and on nuance. Rigid rows and exact keyword matches cannot process the actual meaning behind our words. To give an AI a functioning memory, we have to abandon systems built exclusively for syntax. We need an architecture built entirely around semantic meaning. This requires a completely different approach to data. It requires vectors and embeddings. Before data goes into the database, it passes through an embedding model. This model analyzes a piece of unstructured data, like a word, an image, or a company policy, and translates its semantic meaning into a long array of floating point numbers. That array acts as a specific set of coordinates. It plots your piece of data as a single point inside a massive, multidimensional mathematical space. The defining rule of this environment is spatial geometry. Concepts that share similar meanings are clustered physically close to one another. Conversely, a concept that is entirely unrelated is pushed far away to the other side of the space. When you search for a concept, the database uses a metric called cosine similarity. It measures the angle between the coordinates. A narrow angle confirms that the two pieces of data are highly relevant to each other. By converting unstructured ideas into spatial coordinates, computers bypass syntax completely. They calculate human context as a mathematical certainty. There is a scaling problem here. Calculating the exact distance between a user's prompt and millions of stored vectors one by one would take far too long for a real-time AI conversation. To solve this, vector databases use an index algorithm called HNSW. It skips the exhaustive scanning process by organizing the vector space into a multi-layered hierarchy. When a query enters the system, it starts at the sparse top layer. Because there are very few points here, the query zips across long-range connections to quickly reach the correct general neighborhood. Once it finds the right area, it drops down into the denser middle layer, using shorter connections to refine the search. Finally, it drops to the dense bottom layer, where it instantly locks on to the closest possible match to your original prompt. This layered architecture dramatically reduces the computational workload. It allows complex AI systems to navigate massive data sets and retrieve highly accurate memories in milliseconds. When we connect this high-speed vector database to a large language model, the architecture is complete. This pairing is called Retrieval-Augmented Generation, or RAG. It provides the AI with an infallible long-term knowledge base. Here is how it works. When you ask a question, the system pauses. The vector database bypasses the LLM's frozen training data, scans your proprietary documents, and instantly finds the most relevant context for that specific prompt. Then, milliseconds before the AI generates its answer, the system injects that exact context directly into the AI's working memory. The model reads your internal data and drafts a response based solely on what it just retrieved. Because the answer is mathematically anchored to your verified facts, the hallucination problem is neutralized. As powerful as this is, the most effective retrieval systems running today do not rely on vectors alone. They use hybrid search. This technique merges the semantic understanding of vectors with the exact match precision of traditional keyword filtering. Hybrid search allows a user to search a database for a conceptual vibe or idea, while simultaneously enforcing strict, hard data constraints, like a specific upload date or a maximum price. We have moved past algorithms that crash when they forget the premise of a question. By utilizing embeddings and distance metrics and layered indexing, we now operate systems fully grounded in continuous, proprietary context. Vector databases allow machines to map, navigate, and finally retrieve human meaning.